So 11.7, calculus of vector valued functions. There's a lot of words on this page. It's all screen captured from the beginning of the section in the textbook. A couple of things that I pointed out to myself is simply, here's a highlighter, techniques of single variable calculus, which is what we've been doing, carry over with very little change. Okay, so again, limits, derivatives, etc., integrals, all is going to work. The new and important part is just the geometric interpretation. So there are some really great Khan Academy videos that have the different vectors and the graphs being sketched and showing how that very small change has that position vector approaching with the limit, as we're going to see in a little bit, and derivative, etc., tangent lines, and all of that. So the graph of it looks a little bit different. That's about it. Okay. So this diagram, this sketch here, is showing the vector valued function r of t approaches u as t approaches t initial. So the direction of that r of t, that parametric, is approaching this vector u, and that is just showing that our limit definition is equal to that value as well. Okay, we will use that when we find our derivative, etc. So just like in chapters 2 merging into 3, we used our limit definition. If we thought of things that changed just a little bit, like if we forced that indeterminate form, that 0 over 0, then we would have our exact rate of change, our exact derivative.
Can you zoom out a bit?
Yes, I can zoom back out. Yep. And then the last part of this, right, vector valued limits are computed component-wise. That's what's happening with all this stuff. We want to make sure that we're taking a look at the x term or x component as well as the y component. So you're always going to find the limit of each of those. You're going to derive each of those. You're going to integrate each of those separately. Okay? And within there, they're different parameters essentially, right? So they're different functions or expressions that you can find the limit of, derive, and integrate. All right, so first one, example 1, calculate the limit. And this textbook uses the capital R, not the capital R, the bolded R, signifying that it is a vector. Sometimes, like in the Khan, he puts a little vector symbol above it. There's different ways to notate it. Most commonly, it's the bold R. That's a little bit hard for me to write, but just to understand that when I'm writing R of t in this section, it is for the vector. So we want to find the limit as t approaches 3, where R of t is equal to t squared and comma 1 minus t for the x and y components. So we are simply taking the limit of each component. So the limit of bolded R of t as t approaches 3 is equivalent to the limit as t approaches 3 of, let's see, it's t squared, comma 1 minus t, which is equal to, if I evaluate t squared at 3, it's continuous. There's no reason I can't just do direct substitution. And I get 9. And same idea, 1 minus t continuous, I get negative 2. Done. Okay? So those components individually were continuous. Therefore, I can just evaluate the limit. Limit matches the value of that component. So just like we saw again when we went from chapters 2 to chapter 3, we said, well, the derivative, which could be notated as d of dt, the change in rate with respect to t of this vector, if we use our limit definition, it's that same idea of if we have that really small change in h, we're creating that indeterminate form. We're basically creating no change in our numerator, no change in our denominator, and they are equal to each other. If you want to see the proof, if you want to see the drawn-out explanation, the Khan Academy videos are pretty good. But you don't need them. You won't be asked for that. But what we will apply is simply, if I want the derivative of the vector, I can derive each term, each component. I can even do the second derivative at a moment. And we'll do that in a moment. I didn't turn my AC on. I did resort to windows, and it eventually cooled off last night, but it was hot. All right, here we go. So our double prime of 3, where r of t is written as ln t comma t. So first derivative would be 1 over t, comma 1. Right? Each one separately. Second derivative, t to the negative 1, I'll think of it as, so it goes to negative t to the negative 2, comma 0. R double prime at 3. So that would be negative 1/9, comma 0. Done. Okay. A very simple application of like first and second derivatives. Why not say, hey, here's a position vector. What's my velocity vector? What's my acceleration? Right? Same types of questions could be posed with first and second derivatives with vectors. More wonderful rules that say all of our differentiation rules still apply. Our sum, our constant multiple, our product, our chain, all of them are the same. We just do them component-wise, right? Each one. Right? So if it's a sum, derive each term. If it's a coefficient, pull it out. If it's a product, fr prime, f prime r. And if it's a chain, outer prime, this one's written backwards for the way I always document it. There's my inner prime, outer prime of original. Okay. So, give you guys a second, but we're looking at r and f. So r is t squared comma 5t. F is just the function e to the 3t. All right, so in this case, if I want to derive this product rule, I always do f prime r plus fr prime. I think the book originally defined it, as it is here, defining it in the opposite order. Doesn't matter, obviously, with product rule. So f prime would be 3e to the 3t times my r, which is t squared comma 5t, plus, keep my f, e to the 3t, derive each component of my r, 2t comma 5. Right. I can simplify this, right? I do have a common factor of e to the 3t, that's fine. I can put my coefficient, my 3, inside of this vector, and I can also add my components together. So I could come up with a final answer of e to the 3t times, we would have a 3t squared plus the 2t for our first component, comma, e to the 3t times 15t plus 5 for our second component.
How simplified do we need these?
I would venture to guess that this would be like a multiple choice question, so you would look at your answer choices and go from there. If it were a free response, they probably would ask you to evaluate it at a moment, and then you have your answer there. Part B, using the same f and r, is the chain rule. What is the derivative of r is the outer of f of t? So we need r prime of f of t times f prime of t. So r prime, we did it over here, 2t comma 5, but now we need r prime of f. So wherever the t was in the r prime becomes e to the 3t, right? So r prime, each component, t squared goes to t times some input. My new input is all of f. So it would become 2 times e to the 3t, comma, 5t derives to 5, so there is no composition there. So that first part, this is my r prime of f of t. Now I just multiply it by f prime of t, which is 3e to the 3t. Zoom back out, sure. I try to keep it balanced for everybody at home, too. Is that good for everybody? I can simplify this by putting the 3e to the 3t into both terms. So my final answer would be 6e to the 6t, comma, 15e to the 3t. This slide is a little repetitive to what we've already spoke about, but it's introducing our tangent line at r. So the derivative as a tangent vector. Up top, product rule for dot product. It still is r times r1 original times r2 prime plus r1 prime times r2. So it still follows that same f g prime plus f prime g. So that's just an additional thing up there for specific to dot products. Moving down here, again, it is repetitive because it's the same concept. If we have the change in r over the change in t, we have that really small change, which is virtually 0, over the change h, which virtually 0, will give us our slope. And that's what we're headed towards. We can come up with our tangent line, L of t, where we do r of t0, which is our initial, times t, times r prime, which is our slope. The book has some nice pictures here. I didn't grab them. There's quite a few of them, but just to show how this tangent plays a role, what it looks like. So I've given the graph, plot r of t is equal to cosine t, comma sine t, together with its tangent vectors at t is equal to pi over 4 and 3 pi over 2. Okay? Find a parametrization of the tangent line at t is equal to pi over 4. Okay? So plot is given. Our focus is right here. So similar to the thought process that we had all year. If we're looking for that tangent line, we are thinking point slope line. So same type of process, right? I'm going to come up with my derivative first for my slope. So my r prime of t becomes negative sine t, comma, cosine t. My derivative at pi over 4 would be equal to negative root 2 over 2, comma, positive root 2 over 2. All right, so there's our slope. Our point, r at pi over 4, would be root 2 over 2, root 2 over 2. So our line, written in form of the definition first, would be r, oops, I should write that as L of pi over 4 is equal to r of pi over 4 plus r prime at pi over 4 times t. Right? So that's equal to root 2 over 2, comma, root 2 over 2 plus negative root 2 over 2, comma, root 2 over 2 t. Same idea, like it's just, here's the one value, and then here's a little bit more with our tangent line, depending on what the t value ends up being. Horizontal tangent vectors on the cycloid. So again, nice picture given. The function r of t is equal to t minus sine t, comma, 1 minus cosine t. Find the points where r prime of t is horizontal and non-zero, and then where r prime of t is the 0 vector. So a little interpretation here, but still we always have to start with what's our derivative, what's our slope, basically. So r prime is 1 minus cos t, and the other component is positive sine t. So remember, these are like x and y components. So what would zero this out? If we're talking slope.
How can it be horizontal and not zero?
Quickly, is that a t minus sine t?
That
T
is
minus
a,
cosine t?
up top here is t minus sine t, and then 1 minus sine t. Oh, I'm sorry, no, I said that wrong. T minus sine t, 1 minus cosine t.
Okay, thank you.
You are welcome. So what component here would cause us to have a horizontal tangent?
Sine t equals 0.
Sine t equals 0. Yes, the y component. Think of it, most simply put, as change in y over change in x. What part of the fraction needs to be 0 to have horizontal? What part of the fraction would need to be 0 to have vertical, right? So numerator versus denominator, y component in this case. So we.
But it says non-zero.
The vector is non-zero. I'm going to show you the difference there.
Oh.
It's still horizontal, and if you look here in the image, we still could have 0 slope, 0 slope, 0 slope, 0 slope, but you can see how the odds and the evens look different. Let's investigate. So sine t equaling 0, that occurs at all the pi's, right?
Yeah.
0, pi, 2 pi, etc. Right? So let's investigate a little bit, right? Because it's not just about the slope, it's about the point as well. So r of 0, if I evaluate from the original vector, 0 minus sine 0 is 0. 1 minus cos 0 is 0. And the derivative at 0 is also 1 minus cos 0 is 0, comma, sine 0 is 0, is also 0. So that is causing a 0 vector. Whereas if I do r of pi, just as another example, now if I do the original, pi minus sine of pi is 0, but I still have that pi in there. And 1 minus cosec pi, that's 1 minus negative 1, that's 2. And r prime at pi, well, that one is going to be 1 minus cos at pi, so that's 2. And sine at pi is 0. So this does have a 0 slope for the horizontal, as we already had talked about, right? 0 slope for the y component, causing it horizontal slope.
But in the original, function,
Okay.
it's the slope of the vector is not 0. Why is that? Like r of pi, like the vector still goes
That's-
at an angle.
This is like a position,
Oh,
right? Like this is
Yeah.
more of like the position, and this is the slope. So if we look at the graph now that we have a little bit more information, at pi, there's our point, right? Isn't that the point?
oh, so that is a vector.
That is the blue line is the vector.
So only
At pi comma 2, that's the position, and the direction has a slope of 0.
So the derivative is the vector, but the original is the position.
Sure. We're correct. We're graphing the linear tangent as a vector.
Okay.
Okay? The original is more like that cycloid, points on the cycloid, and we're making a tangent using vectors as opposed to rectangular.
That makes sense.
So I think this goes back to Anne's question from before. Position, kind of direction with that flat slope, that horizontal. Whereas at 2 pi, my position is at 0. My slope is at 0. I have a 0 vector. Doesn't go anywhere. Okay? So I can summarize the questions that were being asked because of our, a cyclical pattern, right? So we can say that r prime of t is horizontal and non-zero for the odd pi's. And that's the answer to question A. And part B is, where's that 0 vector at? Well, that's going to happen at our even pi's, at 0, 2 pi, etc. Vector valued integration, surprise, surprise. I'll zoom in here for a moment. But it says do the same thing, right? Integrate each component separately. So there's a quick example of what that would look like. We can even do definite integrals and evaluate from A to B. Same rules need to apply, right? If you can anti-derive it, you better be able to derive it back to what you started with. There's some constant c involved potentially, right? So all of these things hold true as did in chapter 5. I'm zooming back out so it's all there. Fundamental theorem of calculus for vector valued functions. There it is again. A to B, of R of t is equal to big R of b minus big R of a. So everything above it is just setting the stage for what we already knew. And you do each component. Zoom in on theorem 4. Stop this recording. All right, so the graph is sort of an afterthought. It will be pertain to the solution that we're about to find. Let me see if I can simplify it no, I can't. It's right, it's a PDF. Okay, so the question says finding position via vector valued differential equations. So the path of a particle satisfies this. So the rate is given. Find the particle's location at t is equal to 4 if r of 0 equals 4, 1. Right? We're given an initial condition. We're given a rate. We go ahead and integrate this, and then we'll be able to solve for our c. So we can start by saying,
Read out the formula.
yes, I can. So the formula says dr over dt is equal to 1 minus 6 sine of 3t, comma, 1/5 t. And you're welcome. We are looking for the location at 4 if r0 equals 4, 1. All right, so that means we could make a statement that r of t, bolded r, would be equal to the integral, the indefinite integral, of 1 minus 6 sine 3t, comma, 1/5 t dt. We integrate both components separately. You don't have to write it another step, just do it. So we would get t plus, nope, t plus,
2 cosine?
yeah, 2. So it would be 6 cos 3t divided by 3. So 2 cos 3t, comma, 1/10 t squared. Plus c. All right, so now this is where we say, well, we know that r of 0 equals 4, 1. Okay, so then 4, 1 equals, putting 0 in for our t's, 0 plus 2 cos at 0, comma, 0, plus c. So 0 plus 2 cos 0 would be 2. So 4, 1 equals 2, comma, 0 plus c. So then c has to be 2, 1.
This is the most fun I've had in math so far.
Most fun, I told you. And look at that cool graph. I think it's kind of fun. All right, so we're not done yet, though. The fun's not over. We now can say that r of t equals t plus 2 cos 3t, comma, 1/10 t squared plus 2, 1. Then we put it in. R of t equals t plus 2 cos 3t plus 2, comma, 1/10 t squared plus 1. Then, right, the final question was find the particle's location at 4. Now we finally have our full equation. We want to know, well, what's going on? Where are we at 4? So this is a calculator, but it's 4 plus 2 cos 12 plus another 2, comma, 1/10 times 4 squared, 16, plus a 1. And that is what calculates out to be 7.69 comma 2.6, right? And if we looked at the graph of it, let me zoom so you can see everything at the same time. Here is your beautiful graph showing our initial, right, where we started, when time was 0. So it's a vector, but with the parameter t involved, right? So as time changes, this is where we're headed. And when we get to 4 seconds, we're over there at 7.69 comma 2.6.
Can you zoom in on
Yeah.
The writing?
yeah, thank you.
You are welcome.